Okay, I'll go over the district system and then we'll break for lunch. This is a system that was done in just north of Vancouver. Oops. And basically looking at where it's located, this is the city of Vancouver, and this is just basically almost a bedroom community. People are starting to treat it as a bedroom community, even though it's about a 40-minute ferry ride into Vancouver. People will come in and have an apartment in Vancouver, and they'll spend most of the weekend in the beautiful little town of Gibson. And West Coast, typical, very, very green-oriented, that kind of thing, a lot of forests and all that kind of stuff. So they're looking at ways to stay green or get greener. What they're building over the next 10 or 15 years is a development that's about roughly 200 acres. And phase one has been mostly done already. Over time, they're going to be building about 750 homes. And the town happens to own a hockey arena right here. And there's going to be some commercial space and commercial space over here. So basically looking at one of the differences between if you're looking at individual heat exchangers for houses versus for commercial buildings, houses are typically driven by the climate as much as anything else. The occupancy is going to change it a little bit, but not anywhere near as much as you would with a commercial building. Here, each of you are putting out about 200 or 400 BTU per hour, and you're adding to the cooling load of this building. That's why buildings like this are often cooling dominant. Different types of ground heat exchangers, whether it's a vertical loop or a horizontal loop, or whether you've got the body of water to play with or whatever. And again, looking at the design process, looking at what's different about it. Here you're looking at a finite mass of dirt to play with. Again, looking at the design methodology. So what we looked at on that site was when they first asked for the feasibility study, they didn't have any idea of what kind of homes are going to be on there. And other than they're going to be about this size, going to be about this many of this kind and this kind. They had gotten to that point. No idea what the losses were on typical house. So this puts you you're looking at a ground heat exchanger designed for something like this. It's almost in some respects easier because you're taking the role of the utility almost. How much energy is a typical house going to take on this? Get some gross numbers, and you probably want to put a safety factor on there to some extent. And you don't have to worry about the heat loss and heat gain of each particular house at this point. You have to know about what they're going to be, but lifestyle, and you don't know what's going to happen in that building. And the commercial space is even crazier because today what's a lighting store could be a dress store tomorrow. So loads are going to change awful lot. But overall, if you're looking at the big picture, they know that typical square foot of building is going to need this much energy. But if it's a commercial building, or this much if it's a residential building, or this much if it's an apartment building. So those, you can design how much energy you're going to need for that community. So basically looked at different types of buildings and looked at a typical house sizes that they were looking at, heat loss, annual equivalent full load hours, cooling load, full load hours, and did our best guess at what those were going to be. And then looked at how many of each they were going to build. In the first phase, they were going to build 133 homes, looked at what the total heating and cooling loads were, and designed enough ground loop based on that. Again, looking at the size of the ground loop, at what point, how big do you want to make this? How big can you afford to make this? And at what temperature do you want to allow it to get up to and drop down to in the winter? And if you can balance the loads in one way or the other, and that's where things like the heat sources like hockey arenas or data centers or whatever else, commercial buildings can be a heat source for buildings. That can help make a district system a lot more effective simply because it helps balance the loads. A couple constraints on this particular site. Some of these lots were very, very small. They're only about 49 feet wide by 92 feet long. The only thing that would work on those if you wanted to do an individual ground heat exchanger for each one was vertical loop. The problem that they had was that the town's drinking water directly below that was a layer of confining clay, and they were very hesitant to allow anybody to poke holes in that confining layer of clay to either potentially let fluid from the heat exchanger leak into the aquifer. Again, a pretty small risk, but there's no way anybody can guarantee that it's not going to happen. And prevent surface water from, if it's not properly grouted, from filtrating into the aquifer. That was probably a bigger concern. So they were not going to allow anybody to drill vertical boreholes on that site, but they wanted to go green. They didn't have enough space to do horizontal ones. So the only option that would be potentially feasible, and that's why we were we were asked to look at, is it feasible to do a district system for these zones? When we looked at what was all in there, looked at how the houses were being built, found that there were some green areas here. These are about 700 feet long. This is about 1,400 feet long. They got about a bit over an acre of land right here for a small park. So the question then became, can we put enough horizontal ground loop in those areas to service 133 homes? So future phases, and then there happened to be this hockey arena in here, and this commercial development. Again, commercial development, this is a relatively benign climate. I think the design temperature is about 20 degrees Fahrenheit. It's probably certainly warmer than here. And it doesn't get that hot in the summertime, so if we were ever going to try it anywhere, this would probably be a very easy place to try it, because the temperatures never got that really cold, and the cooling loads never got all that really high. And again, one thing that helped this area, it's a fairly wet climate. It's almost rainforest kind of stuff, a lot of rain. So that we knew that that would help keep the ground wet and the heat transfer properties a bit better. And again, we also looked at the potential of eventually connecting cooling tower, eliminating the cooling tower on the hockey rink, dumping that heat into the ground once it gets into this area. So looking at those different factors on there, if we're looking at just the homes, they typically in that kind of climate they open the windows to get the air conditioning. It doesn't get that hot very often. Peak cooling loads, if they do use it, could be fairly high, higher than the peak heating loads, but there's so few of those days that that's going to happen, almost negligible. Once you start adding the energy from a typical hockey arena in there, they have to get rid of about 1.5 million to 2 million kilowatt hours of energy per year once you consider the heat taken from the ice plus the compressor heat. That has to go somewhere to the cooling, typically through a cooling tower. And once you look at the energy loads on these particular houses, that is enough to heat about 190 to 250 homes for how much energy they're going to extract from the ground. We're putting that much in, and each house is only going to extract that much. So the hockey arena itself would be able to provide enough for about a quarter of the homes in that development. The other thing that they had is this development had to eventually be serviced with stormwater drains, and this was the route that they were planning to take. This from here, from the ocean level up to here, is about a 300-foot rise. Simply adding a heat exchanger at some point in here, ocean water we knew was going to be about 50 to 55 degrees year-round, and we could use that to moderate the temperature of the ground. But when this gets completely built, if the buildings that are going in there weren't quite what we expected, if it became heating dominant or cooling dominant, this could be basically the pressure relief valve on it. If it got too hot, this is a beautiful temperature to dump heat into. If it became too cold, we can still extract a fair bit of energy from this, simply by running the fluid from the ground loop through a heat exchanger and running ocean water through the other side of it. And then adding the other thing that could help as well, the other thing that would, and this may or may not go in at some point. At some point they haven't installed the stormwater drains yet, but when they do, that would be a good time to make that kind of connection. Excavation is being done anyway. There's no big panic for it. So that may happen in a year, it might happen in 3 years. And then the other thing that can do is if they've got the ocean water here, they're looking at a waterfront development right over here, that they can use the ocean water there as well. So the system design itself, there's a connection to the proposed stopping center. And this basically represents the pump house. And here's the ground heat exchanger arrays in the mechanical schematic for this pump house. There's about, I think there's about 14 of them that are going to be eventually in there. And then there's connections that run from the pump house to run down the street. There are 6 and 8 inch pipes that are running down the street that the homes can connect to. As that spans, there can be a connection between this pump house and this pump house and this pump house. So if this one is heating dominant and this one's cooling dominant, they can swap energy back and forth. And this is the one where the waterfront hotels would be, and this is where the ice rink would be. So this one is probably going to get too warm, so they can dump energy over here and dump energy over here. Swap it back and forth. So looking at the thermal conductivity of the ground, just simply measuring the thermal conductivity in backhoe pits, and looking at different ways of getting pipe in the ground. Big wide trench, horizontal drilling, slinkies, and looked at also being able to follow the system. And the problem with this one was that the company that was able to do this wasn't anywhere near this area. They were probably about 2,000 miles away. Getting them up there and mobilizing them for half a dozen ground heat exchanger modules was going to be cost prohibitive. Could have been done, but then they could do it, had the technology to do it, but just get there and do it cost a lot. We were initially told by contractors that this would be the easiest way to do excavate a 40-foot wide trench, lay the pipe in, and they could backhoe it. But once they got into the tenders, none of them opted to do that. We basically designed a ground heat exchanger. You can do this, or you can do this, or you can do this. Take your pick, whichever is the most cost effective. There's no reason that you have to stick with a specific type of ground heat exchanger configuration. It can be sometimes more cost effective. You've got a school, for example, and you've got enough land area to do a horizontal loop. It's amazing how that can sharpen the pencil of drillers in the area. If they, and there's no reason that you can't design a vertical ground loop. If they want to do that, knock yourselves out. Here's how much drilling you're going to need. You want to do a horizontal? Guess what? You can do it this way, whatever way you want. Whatever way you find most cost effective for you. That opens it up to more contractors that can bid on the project. That can get the pricing a lot more competitive. Looking at the different horizontal drilling, looking at what that does to the how much land area you'd need with or without the heat rejection from the ice rink. Looking at if we looked at what kind of we're looking at a slinky system, what depth was most appropriate, whether it's 5 feet or 6 feet or whatever. Looked at different configurations, ended up picking one of those, whichever was most cost effective. The way the system itself is designed and the way it was built, Town built the pump house. There's a header. All there is in here is a header, pumps for the ground heat exchanger. Ground heat exchanger modules can be built as they're needed. As if they only built 40 houses this year, they may only need 2 of the modules. Built 250 homes in the next couple of years, they may need another 6 of them. And it's designed so that they can connect up to it whenever they want. Distribution lines, they simply go down the street. The way it was designed is that supply line goes all the way around a loop and back onto the supply line. Turn line is connected up to the turn line, goes all the way around. That allows you to isolate this section. These heat pumps can be fed from this end, can be fed from this end, and return goes back this way and this way. Yep. Yeah. There's a couple of ways that they looked at. One was basically looking at a flat rate per square foot of house. and charge you so many cents a square foot for your energy. What they're going to end up doing, and I don't think they've done it yet, is that they'll put an energy meter on each house, and they'll charge you for every BTU pull out of it or put into it. And the economics actually works pretty good in that particular area. But coming to that right away. It's kind of interesting because the town can make the rules. The town owns the ground loop and the pump house. They own the distribution piping. Developer put in the piping under the streets, distribute the heating and cooling, same as they would the water lines and sewer lines. And basically it's going to be built over the next 10 or 15 years, and you've got time to see how the system is operating. And if it is taking more than we need, then simply look at ways to add the system. They may or may not end up doing the connection to the ocean, depending on how the system is operating. If they're going to connect a couple of schools to it and expand the system eventually, they may do that 10 or 15 rather than 5 years. So there's enough time. Like, you don't know. It's no different than a gas utility putting pipelines down. They're going to oversize it to some extent. But if there's a huge development that's going to come in down the street, and the gas company wants that as a client, they may expand the gas line and make the adjustment. Yeah, there's enough leeway on there, and the town can set the rules. Here's what you can and can't do on your house. Here's how you have to build it. Here's the building codes have to meet requirements. So you know that that's going to come into roughly so many BTU per hour per square foot, and then you can do the loads accordingly, base it on that. And then if things change, then that client uses more energy from the ground or puts more energy into the ground, they're going to end up paying more. It's no different than any other utility, and it's no different than talking what the electric utility has to do, determine how big the transformers have to be for this development. And if they screw up on that, they have to change it. But you can design it to the best of your knowledge with the information that you have, and then hope that it ends up going that direction or adjust it accordingly. So this is the inside of the pump house. The only pumping that's in the pump house right now, and at this point there are only 3 heat exchanger modules connected to it. There's a pump on each one, and that pump comes on based on, these pumps come on based on what the temperature is inside this common header. This is where the distribution lines are going. This one is connected aren't yet. And the pumps for the heat pumps in the homes, each house has, there's a curb stop valve just like there would be at the water line or sewer line, or water line there. And there'll be an energy meter on there, and there's a pump house. What happens inside of the home is going to be no different than what a contractor would see on a typical home. For example, what they see inside of the home, you'll see a pair of 1.25" lines coming into the house, and you'll connect a standard everyday pump module to it. The only thing that's different is the energy meter, flow regulator valve, curb stop valve, pumps, whatever kind of heat pumps they want to put in there, they can put in there. Like you can buy whatever gas furnace you want if you're connected to the gas line. They can put in whatever kind of heat they want to put in. Then this, there are a set of guidelines as to how you connect up to this. The town has to make this connection so that it makes it more difficult or more challenging for somebody to screw up the whole fluid system. Can it be screwed up? Sure. Somebody screwed up the gas line? For sure. So metering the energy, basically looking at the, and yet we were able to price some flow meters, and I think they've come down in price since then. They're about $700 a house. The meter reader comes by once a month, reads the meter through a radio frequency transmitter, and sends them a bill. They already drive down the street because they buy the water. So the economics of it, basically, the geothermal system, looking at the energy consumption, if they were going to do a geothermal system, was about $980 for this size house. Small house, 460. Townhome, about 340. Equivalent in gas at that time was about these numbers, and electric was more expensive. And for the geothermal utility to get their money back, that was set up so they could make the numbers work, so that this is about the equivalent of the homeowner pays the cost of electricity and the bill that they get from the town from the geothermal utility. That was about 5% or 10% less than running the system with gas. So there's a benefit to the homeowner in about a 10% reduction in energy cost projected. And then there was no additional capital cost because they didn't have to pay to put the ground heat exchanger in place. Somebody else that amortized the same way as somebody building a nuclear plant or a coal generating station or whatever, and the infrastructure to deliver to your home. Yeah, they're in that climate, yes. They've got about, I think, 20% propylene glycol. Unfortunately, they had to go with propylene glycol, which makes the pumping a little more difficult and makes it more expensive. A lot of fluid in there. So I can't remember how there's already a couple kilometers of 6 and 8 inch pipe in. Total cost of building it, or the geothermal utility bill, homeowner should see a slight saving in energy cost. Won't have an air-cooled condenser in the backyard. They want air conditioning, and they will pay a little. They won't have to pay any more capital cost. I think the capital cost was worked out to fairly close to the same thing. About $800 difference on this. 500 to $800. Yep. They talked about it. I don't think they ever looked at it very seriously because the problem with the district heating system like that, where you're delivering hot and chilled water, is the distribution system gets a lot more expensive. And then the pumping system, the cost of the heat pumps that can produce that kind of hot water, not a huge saving overall. That cost is transferred over to the home, instead of the homeowner paying for the heat pumps, utilities paying for the heat pumps. This just seemed like a much easier system to design for sure. And I know hot water district systems are fairly common in Europe. They are fairly common in parts of North America. I think New York has one. Ball State University has a heat pump system like that. Here we can use the distribution system can be simple high density poly pipe on. So putting the piping is the distribution piping is fairly inexpensive. Yep. Yeah, and we did look at that. In retrospect, probably I would look at it a lot harder. This was originally started on about 5 or 6 or 7 years ago. I know there's a fellow in Missouri that does a lot of work with a single pipe system, does it very well, Kirk Mesher. And I think it's a good system. Might have probably been more cost effective. And even at peak loads, you might only be looking at about, if you designed it properly, it might only be a 5-degree temperature difference from one end to the other. Would have been fine, I think. Again, if you want to look at, we've got a bit of redundancy built into the system. We can isolate 5 or 10 or as many homes as we want with this kind of system. I don't know if you could do that with that. You have to think about it. Okay. We thought our thought process was that all the distribution piping is just more heat exchanger anyway. And for the, I don't think any of the John heat exchanger module pumps came on for the first 6 months after, when there's only a dozen houses on it. Just the piping under the streets was enough to service them because there's so much volume of pipe in there, and it is, yeah. Be a different here, different in Winnipeg for sure. That was why it was a really good place to try it. I think there's going to see more of those kinds of systems in the right place. Yeah, this is a two-pipe system. And so basically there's a supply line and a return line. Single pipe system, there's a single line that this would be a single pipe. And this pump would go from that pipe and dump back into the pipe. This one would get, if it's a very cold day, this one would get slightly colder water. And then there would be a pump in here somewhere that would be circulating this fluid through the ground. If the flow is going this direction, this one would be maybe on a really peak day, it might be 3 or 4 or 5 degrees colder in the winter, and maybe 4 or 5 or 6 degrees warmer in the winter or in summer. Yeah, it's a really simple system to install. You don't have to, it's the same size pipe all the way around, half the pipe to install. One thing that we can do with this system that I'm not sure you could do with a single pipe system is feed the system to both ends. Like, in other words, we can isolate this section here or this section here. We've got a valve here and here. We can isolate these. And these houses can be fed from here, and the return can go back here. These can be fed this like a municipal water supply service. So the way this system was built, the town spent the money on the pump house and ground heat exchanger module. The developer, part of their development agreement was that the developer had to put in these distribution lines and the homeowner, and up to the curb stops. And then from the curb stops, the homeowner was responsible for it, or the builder. Yes, they can't use gas as a primary heating, period. And that's built right into the development agreement. Again, if you've got that leeway where you can make the rules, you don't always have that option. They could, yeah. Or they could, and some people like gas fireplaces or gas barbecues or whatever else. But again, the gas line is going to be a lot smaller. The gas company probably may not want to go into a development like that. That was, I don't think the gas company is going in there at this point yet anyway. Basically the cost of electricity, they can't control that. What they can control is how much money they have to get back to build the capital, to pay for the capital cost of building it and for maintaining it. It was designed for as low maintenance as possible. The only pumps that are responsibility of the town are the pumps that are for the ground heat exchanger. One of these pumps breaks down, they're all designed for exactly the same pump. Spare pump in there can be replaced fairly easily. And there's not a lot of different pump sizes on there. They're all, I think, horsepower pumps thereabouts. And they would, if one fails, it's not the end of the world. So we're expecting fairly good reliability. And again, working with the town developer, they're the ones that really pushed on and suggested on this kind of piping system where you can feed it from both ends. Give it a bit more redundancy in the system. The town is responsible up to the curb stops. The town was able to get the incentives from some incentives for this because the problem with a system like this, somebody has to spend an awful lot of money building the pump house and building the ground heat exchange modules, and the houses aren't going to be built for gradually built up over 5, 10, 15 years. So somebody has to put a lot of upfront cost in there. They amortize that over 20 years, I think it was. So they're comfortable with that. The system that their capital costs are covered. No, they're getting their money back No, they're getting their money back from the fees that as the geothermal utility. They meter the energy going in and out of every house, and that the energy bill for each and every house is based on or the energy cost is based on the energy meter. Well, no, the town is treating this as a revenue source. It's a utility. No, no. They got some incentives from the province. They got some incentives from the province to help the upfront costs, because they had to spend a fair bit of money on design and building the heat exchangers before they had any revenue, probably a year before they had any revenue. Exactly. Eventually it will cover it, but they're looking at probably roughly 20 years. The town had some of their own financing, and then they got some incentives from the province. Yeah. 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 That's right. Yeah. Yeah. No. It should be self-sustaining. That's the way it's hopefully designed. Yep. BC has made rules for municipalities where they have to get more energy efficient. At that time, this was about 6 or 7 years ago. I think the carbon tax was just in place. I don't know if it had much of an impact on there, but policies of the provincial government. That's why they had the incentive. That most of them are going to be forced air, water to air heat pumps. Typically, very similar to what you would see as a contractor if you were putting a geothermal system with a ground loop outside. The difference is that the ground loop is down the street from you in the park area. Nope. Super or electric, yeah. Yeah. No, just the electric utility connects up the power lines like they normally would. Again, it's something that probably could help, but again, with heat pumps, that can sometimes be an issue. But I don't think there was anything special done for that. Yep. 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 And what the cost per home, the town spent about $4,500 to put the ground loop in when all 133 homes are connected. It's about $4,500 per home. They also spent another about $700 per home to build the pump house, and the developer spent about $2,300, $2,400 per house to run the pipes down the street for 75 homes. And as this expands, there'll be another loop and another loop and whatever. And the developer, with the development agreement, you want this development to go ahead, and then guess what? Here's what you're going to have. Yep, that's fine. They put it into, they had some walking trails that went through the town and also a park area, and that's where they put the ground. I don't know. I think they may have borrowed some money specifically for this project. I could be lying about that though. I don't know. I'm not 100% sure on that. I know that it's sort of a decentralized pumping system where you've got each ground heat exchanger module has its own circulation pump. Yep. Based on temperature and yep. Yeah. Well, and these are actually the piping is sized. You might have maybe 20, 30, 40 homes on one loop, and it's just little flow circulators. That typically what you'd see with on a residential system. That's it. Just tiny little circulator. The piping is pretty good size. 6 inches is the most common. Yep. Yeah, even when all the houses on there, it's designed so that they will be within probably under 20 feet of head for the ground loop. And they're pumping from here, and this house might be 1,000 feet away, 1,500 feet away. So we can cover a fair bit of ground with this one pumping station can handle, we figure, about 275, 300 homes with the amount of ground loop that they can put on there and with the amount of connections they can make on this side of it. And then when they want to expand that to another part of the development, they'll just build another one and connect this pump house from the other pump house, so if this one gets too warm or cold, they can swap energy back and forth. Yep. Purging it was the contractor had a bit of a challenge on there. Pumping, getting air out of 6 and 8 inch pipes needs a fairly stout pump. And we told him that, and eventually he ended up buying a pump big enough to do that. It's not complicated. You need this many gallons a minute. But yeah, that certainly is something that you have to consider when you're designing a system. How are you going to get the air out of the system for sure? You have to be able to facilitate, make it as easy as possible for the contractors. And again, it's got to be aware of flushing 8 inch pipe, and you need to know where you want to put valves. Yes. These first houses went in probably 5 years ago. And I think they're up to about, it hasn't grown as fast as they had hoped. I think they're up to about 100 and some odd homes. Yeah, they haven't talked to them for a bit, but their temperatures are running well within the range that they can operate at, and their energy costs are similar to what we projected. Not far off, based on looking at current energy rates and electricity rates. Again, the heat losses and that are relatively simple to calculate on a residential application. They haven't, the commercial system that's over this area right here hasn't been built yet. Hockey rink hasn't been connected yet because they haven't grown as fast as they'd hoped. I started just after the 2008 when they had the downturn of it. BC got hit more than a lot of places. So they pre-built the slinkies like this, laid them in. This contractor decided the easiest way to put the slinkies when just a backhoe trench on there. Other contractors might have ripped up all the ground and just laid a whole bunch in, but it really depends on what the contractor wants. And the pump house is built with here's the ground heat exchanger modules connections and piping. So look at the overall income revenue from the chart shows an investment of $695,000, 5% interest. The problem is, like I said earlier, there's a gap between when they start getting revenue, get enough revenue to pay for that, and that's what the incentives for the province help cover. So once they get these houses connected, they'll have a revenue of about 70,000. Their annual loan repayment is about 55,000. So at least some for maintenance and things like that. There should be relatively little maintenance. They range from, I think the smallest ones are about 1,200 to 1,500 square feet and up to about a bit over 2,000. Yeah, they could have. Yeah. But yeah, that area gets an awful lot of rain. It rains from probably late October till about the end of March. So it's given me a lot of, I've lived in Vancouver and it gets a lot of rain, kind of like Seattle. So development is well treated, again, looked at ways of avoiding damage. That presented some challenges. He's digging around it. And one thing that you have to be aware of, the developer certainly has to be aware of, and the civil engineers, you're working with civil engineers on this, there's water lines, water supply lines, sanitary sewers, storm sewers, geothermal distribution lines, there's a gas line, and I think, I'm not sure if the gas line has gone in or not. But there's a lot of pipe under the ground. You've got to maintain certain distance between this and that and everything else. So yeah, you do end up working with civil engineers to a large extent as well. Some of the houses that have been built, where they got the lots. I'm not sure what they sell for. Probably Vancouver's not a cheap place to live. It's probably a few $100 grand each. I don't know for sure though. So nice, really pretty community. I could live there. Yeah, but it's pretty. Again, you got to be able to be prepared to get webs on your feet, between your toes, because it does rain a lot there. Okay, thank you.